Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. Today is our lecture number 9, Unit Electrostatics. Our today topic includes electric field and potential gradient. Very important topic, the electron volts. And remember, I have already done the electron volt to you in the previous lecture. So I think we don't need it to do it again. So I will skip this one. The third is the capacitor, capacitance of a parallel plate capacitor. Two cases here, when the medium is vacuum and when the medium is dielectric. So let us start with the name of Allah Almighty. Bismillah Rahman Rahim. Let us come to the first topic, and the first topic is the electric field and the potential gradient. The electric field, I explained the part of the electric field to you in great detail in the right in the beginning of this chapter, right? But here I just want to tell you that the why I wrote here the electric field, because it is important here when I explain the potential gradient. Then for this, that is important to mention it once again. So I, you know, electric field is the natural or the intrinsic property of every charged particle, that around every charged particle there is electric field. But this electric field has what? We have two kinds of difficulty for the electric field while plotting the electric field, yeah, while representing the electric field on the paper. And what are those difficulties? The first difficulty is strength, that very difficult to represent it in its strength and second direction. So because of its strength and direction, it is very difficult to represent the electric field diagrammatically, right? So for alternative to the field lines, we just draw a kind of contour map, right? That is the uh, sorry, I wrote counter, the contour map, right? We will just make the contour map of the electric field, uh, and this contour map, uh, it can be drawn by using the equipotential line, using what? Using the equipotential equipotential lines, particularly for a kind of 2D system, are using equipotential the equipotential surface, right? If the situation is 3D, right? For example, when a kind of like spherical system. So the contour map we will draw to represents the electric field. So what are actually the equipotential line? The equipotential line is in fact the equipotential should be equi, that is for, this is for the 3D, sorry, for the 3D system, right? And the equipotential line, that what are actually the equipotential line? That is, equipotential lines are in fact the line, what? The line where the line which connect, the line which connects points, which connects points in space, point in space where the potential of, where the which have the same potential, which have which have the same potential, right? which have what? Which have the same potential. Our equipotential line is the line where all the points on the line where what? Where potential is the same across all point. Where potential is what? Where potential. Yeah, where all the points are at, where what? Where all the points are at the same potential, right? They are called the equipotential lines. And these equipotential lines are the concentric lines of increasing radii. What? Usually for charge or in 3D system, these are in fact what? The concentric circles are for the 3D space spheres are like of increasing radii. Of what? Of increasing radii, right? As you see. So look, if I just see, look in this diagram, you see that these are the equipotential line. For example, this line, as you see, this line, this line, and this line and this line, we call these lines as the equipotential lines. Where? Why? Because all the potential of every point is the same. If I consider this the positive charge q, and this is also the negative charge q, so the lines are drawn for the positive charge and for the negative charge also. Now one important point which I want to tell you is number one, that is, these lines are actually what? They are drawn perpendicular. What? Perpendicular to the direction of what? Perpendicular to the direction of the electric field intensity, or the electric field E. As you see, look, they are drawn perpendicular everywhere. It is what? It is perpendicular to the direction of what? These lines are perpendicular to the direction of the electric field everywhere, as you see here. So they are drawn perpendicular, right? The square and every. Now why I say that these are the points of equal potential, right? Why equal potential? For example, if I choose any 2 point, let for example, for this equipotential surface, I choose the point A, and if I choose one point, point B, for this, these lines are drawn. This is for the positive charge, this is for the negative charge. Here the red indicates what? Here the red indicates the electric field intensity. Here the blue indicates the electric field intensity, the direction of the electric field intensity for the positive charge. So here you see, look, that is, if you have a test charge, for example, look, if you have a test charge Q naught like this, and if you want to move the test charge Q naught in the direction of A to B, then what will happen? No work done will be required. No work done is required, to move the charge from what? From A to B. A to B. What is the reason? The reason is very simple. It is because of the fact that the potential at the point A is the same as the potential at the point B. Why I'm saying this thing? Let us see here. Do you remember when I was explaining the electric potential to you, the KQ by what? By R. So you see that what actually happening, if you see the potential at the point A, now that is the potential at the point A delta V, let's suppose, for example, if I write, right? So yeah, leave this thing. This is very simple. The potential at the point A will be equal what? K Q into R. And what will be then the potential at the point B? The potential at the point B will be again K Q R. Why? Because in this diagram, if you see point A and point B are at the same distance from the charged particle, both have the same distance. If you just see, look, this distances are and this distances are. So definitely you have the same potential here and you have the same potential here. So if you move perpendicular to the direction of the electric field intensity, then no work done is required. Why? Because that you know that work done, we know that what is that work done from A to B? The work done in fact from A to B is equal to what? If you have the test charge Q naught, you want to move Q naught, and this is equal to delta V. And you see that this Q naught, and what is delta V? VA minus VB. And you know that this VA minus VB is 0 because VA is the same as VB. Let's say V. So what does this means? That the work done is what? It is 0. So there is no work done along what? The direction perpendicular to the direction of the electric field intensity as you move, right, from A to B. So why? Because they have the same potential at the point A. So the electric, that is the equipotential surfaces for the positive charge you see here, for the negative charge you see here, this one. So at every point electric potential is the same. For example, now remember, the potential at this point and at this point is not the same, right? Points on the same line have the same electric potential, right? So since electric potential is a scalar quantity, it can best describe the electric field intensity at every point. And I'm coming to that point, and we call that as the potential gradient. And now look, this is for what? This is for the charge to charge system. Look, the equipotential surfaces line. So here you see the lines are very much closer to each other. So where the lines are closer to each other, here in this case, then the electric field intensity will be what? It will be much more greater. So you see in this case, look, the electric field intensity is greater in this region, the electric field, or this region. Why? Because the equipotential lines are very much closer to each other, right? So that is one of the most important point. Here the electric field intensity is all uniform. Why? Because the lines are equally spaced together, and this is what you will see right now when I explain it to you. So you see, look, this is for the negative charge, this is for the positive and negative charge, and that is for the positive, sorry, the positive, and this is separately for a positive and separately for a negative. So let us apply this thing to here, the second, which the potential gradient, the potential gradient. That what is a potential gradient? In fact, the potential gradient can be defined as it is the rate of change of electric potential with respect to displacement. That is the rate of change, the negative rate of change. I would like to what? The negative rate of change of electric potential, of what? Of electric potential with respect to what? With respect to displacement or position vector. Displacement is called what? Is called the potential gradient. It is called what? The potential gradient. We call it what? We call it the potential gradient. It is called what? It is called the potential gradient. So you see that, look, mathematically we can write that the potential gradient is the equal to, that is the rate of change of electric potential with respect to what? With respect to the position delta R. That is called the potential gradient. What I would like to tell, that is what your book says. Let me tell you that in fact, what does this mean? This tells us that the electric field intensity, right, between 2 points is equal to the negative rate of potential difference with respect to the position. We can describe this thing here. Now, what does the negative sign indicates? The negative sign indicates that the direction of the electric field intensity is opposite to the direction in which the potential is increasing. And now the I will tell you how is it like that. Let us see, let us derive this relationship. Now look, if I just tell you that, see here, look, I am coming to that point, but in order to derive this relationship, I just want to tell you that whatever I did, the equipotential surfaces that were for a single charge are for the non-variable electric field or for the varying electric field. Here for the constant electric field, these are what? These lines are what? These lines are called the equipotential surfaces, where the electric potential is what? The same along this line. For example, let us consider that we have what? Between these two plates, we have a potential difference, what? Delta V. For my convenience, I say that this delta V is at 18 volt, for example, between the plate A and the plate B. Right now you see that the plate B have taken at what? At zero potential. This is our reference line. That is taken at what? It is zero potential. And the plate A is taken at 18 volt, right? And they are separated by a distance D. Right now you just see, for example, look here, if I label it as what? 2 volt, this is 4 volt, this is 6 volt, this is 8 volt, this is 10 volt, and so on, for example. And then you just go, so you see that, look, it these lines, for example, if I just call this line 1, line 2, line 3, line 4, and line 5, for example, you see that every point on the line here, here, we have the potential as 2 volt. Here we have the potential as what? 4 volt. And here we have the potential as what? 6 volt. So what is the potential? Potential is K Q by what? By R. So you see that as you move towards this, the R is decreasing and the potential get increasing. Look, for example, here at this point, what is going to happen? Look, you start from what? Your displacement. For example, this is your zero displacement and this is your maximum displacement. So now as you see, starting from the zero, because we are moving from a point of reference where the potential is zero. So you see that, for example, if you wish to calculate the electric potential at the point 3, so definitely you are moving towards the point 3. So this distance is decreased now. So distance is decreased, the potential must be greater. And you see, look, what is the potential? 6 volt here. Now, if you just compare, look at this point and between this. So you see the potential is what? 4 volt. Why? Because the distance is greater, right? So that is what the potential we have. These for the constant electric field, these are the equipotential lines. So we can draw the equipotential lines for what? For the electric field, that is for the electric field line or intensity for the oppositely charged parallel plates. Now you see that, look, but remember the electric field intensity E, it is the same everywhere. So you see that the electric field intensity is what? It is the same everywhere. But what happens? The potential difference is changed as you move from the plate B towards the plate A, but electric field intensity is the same. Now question, why it is the same? And answer is what? The answer is very easy. Why? Because you see, Look, do not you remember that the electric field intensity for what? For the oppositely charged system is sigma into epsilon naught. So you see that it has no dependence on the R. So electric field intensity is the same, but V is changing, right? V is what? V is changing, and your electric field intensity is what? It is the same everywhere, but potential is not the same everywhere, except along the equipotential lines, right? So you need to understand this thing here. Now let us take that. I want to copy this here so that I should not move again and again. Now look, here, now let us see. Now we want to derive this relationship. So let us consider a charge, right, which Q naught, right? I want to move a charge, what? I want to move a charge Q naught between any 2 points inside the electric field. For my convenience, I would like to do to represent this displacement by delta R, like that, the smaller distances. So as you see, look, A is by the definition of what? A is by the definition of the work done. I want, we have, let me first make that. I want to move a positive charge Q naught like this from this point against the direction of the electric field. So definitely there must be what? So if you want to move the charge against the direction of what? Against the direction of the electric field intensity, let me make like this, positive charge Q naught. So definitely for this charge, what happens? That there must be what? That for the electric field intensity, as I told you, that the electric field intensity E, which is equal to what? Q naught, that is, sorry, the electric field intensity, this is the, sorry, this is the electric direction of the electric field intensity. So you know, on this chart there must be what? That is the force that the charge will experience will be equal to what? Q naught into E. Now, in order to move the charge against the electric field, right, that because for this, there is a force which acts in this direction, the electrostatic force. Definitely, to do work done, we must apply a force on this charge particle. Let me label this as like this one on the green. Okay, so we must apply a force on it, this force, to move it against the electric field from the point of lower potential to a higher potential, say from A to B. Then there must be what? Then there must be a work done. So the, by the definition of what? By the definition of the work done, what is the work done? This work done will be equal to what? It will be equal to F dot delta R, or this work done will be equal to F minus F into delta R. The negative sign indicates that the displacement is in the direction opposite to that of the electrostatic force. And here, this case is different from the electric potential due to a point charge. Here, the force is constant. Why? Because the electric field intensity is the same everywhere. So this is for what? For the constant force. And as this force F is in fact equal to what? The electrostatic force acting on the charged particle. This force is equal to what? This force is equal to this thing. So what will be this work done? Then the work done will be equal to, minus Q naught E into what into delta R, or simply we can say that q that this is equal to what, that this is equal to the q naught, this is equal to, sorry, that this E is equal to what, the work done W into what, from A to B, the work done into q naught, right? Let me do it. That is E is equal to what, it will be equal to the work done into the work done per unit. I'm sorry, class. What had happened to me? I don't know. This delta E delta R is equal to the work done into what? Into uh, Q naught, like that. Work done per unit charge. And you already know that the work done per unit charge is in fact what? The change in the electric potential. And you know that, or what does this mean, that electric field intensity is the negative rate of change of potential with respect to delta R, right? So what does this means, that this is what, this is the potential difference, this is the displacement. So the smaller this distance, the greater will be the electric field uh, intensity between the two plates, right? So if the plate A become closer and closer, then what will happen, the electric field intensity will be what, the electric field intensity will be the greatest for the same potential difference. Remember, if we don't want to change the potential difference, right? So that is the this equation is called the potential gradient equation. Now we can use this equation also to find the potential differences, and very simply we can write that, for mostly we will be using this equation as most simply that E is equal to what, V by D, right? Or we can say V is equal to what, E into D. This is the most common equation used in electrodynamics, very common equation, right? That potential difference is equal to what, electric field intensity into what, into D, right? So that is what, now as I told you already, that electric field intensity is what, that electric field intensity is the same everywhere. Now why? Because if you just see, look at these two equation, and this is very important, and I want to write these two equation here. First, this electric field intensity E equals minus delta V by delta R, right? Or another one which I want to write, V is equal, yeah, delta V is equal to E into what, E into D. So now you just see, as I told you, that electric field intensity is the same everywhere, but it is not necessary that the electric potential will also be the same everywhere inside the plate A and B in this region. Now why? Because let us see, look, this is the region which I want to explain the things in it. Look, as I told you that E is the same everywhere. See here how E the same everywhere. E is what? E is the same, or E is constant everywhere. Now why? Because you know, look, if you decrease the distance, right, delta R, for example, if you just come here, then if you take this point and this point, then what will be the electric potential here? The electric potential will be greater. So smaller the distance, if you increase the distance, the electric potential increases, right? And you have the same E everywhere. This is for the constant electric field system. Now look, but if you choose this point, so what happens here? Actually, the distance is increased. So the potential is what? The potential between then this point and this point. The potential is, look, if you just come here, what happens, for example, is, I already labeled this somewhere. Oh, they left above. This is, for example, 2. This is, for example, say 4. This is, for example, say 8. This is, for example, say 10. And this is, for example, 12, and so on. So now you see, look here, electric field intensity is the same everywhere, but not the electric potential. Electric field intensity is the same. How? For example, if you choose these 2 points here, then look, what is the electric potential? 18 minus 8, 10. But here what happens? The distance is decreased, right? So, and if you just see, the potential is what? Between this red point and this portion, what is the electric potential? For example, the electric potential is 10 volt. But if you would like to see the things here, then look, what is going to happen? What is the electric potential here between this point and this point? The electric potential is what? It is 16. So, but what happens? Here the distance is greater. Potential is greater here, and the distance is also greater. So you have the same E. Here what you have did? The potential is decreased, right? 10, it reaches to 10 volt. But what is the distance? The distance is also decreased. So you have what? So you have the same electric field intensity everywhere, right? You have what? You have the same electric field intensity everywhere. V K into Q by R. So if R increases, what happens? V decreases. If R decreases, V increases. Is it clear? It was for that system. For this, look, as I told you that it is not necessary that if E changes, so we should also change. No, sometime potential may change, but electric field intensity may remain the same. This is something which usually students don't believe, but here I show it to you. Okay, so one is this thing. Is it clear? So I think that I'm so sorry that I couldn't finish the entire lecture for you. So this is all about the potential gradient, and for the capacitor, that is the the next part, that the capacitance of the parallel plate capacitor. Inshallah, I will explain that to you in my next lecture number 9. So thank you very much for being here, and this is our final equation. V equals E into D, or in a totally scalar form. Why? Because electric potential is what? It is all scalar, right? So what we can say, that another interesting point which I want to explain to you. Look, delta V, or the electric potential, is equal to E into delta R or delta D whatsoever. That electric potential is in fact what? That electric potential is the dot product of what? The dot product of electric field intensity. Sorry for taking some extra time. Electric field intensity, electric field intensity, and displacement. And what? And displacement. And I would like to explain it to you, or to elaborate it in most convenient way, that E dot delta R. So if you remember, I told you that there is no work done while moving along the 2 points which are at the same potential difference. Why? Because if you move perpendicular to the direction of the electric field intensity, then what happens? Theta 90 degree. And what is cos of theta? So that is cos of 90 degree, and it is definitely what? It is definitely 0. So what will happen? That is, the delta V will be then equal to E dot delta R into what? Into 0. And what does this means? That delta V is equal to 0. So what does this means? This means that the potent that is that V at A minus VB is equal to 0. What does this means? That VA is equal to what? VB. So this is an alternative method which I show you, that the 2 points are what? That the 2 points are in what? Are at the same potential. They are what? They are at the same potential. So moving along that is the direction perpendicular to the direction of the electric field intensity, no work done is required. Why? Because the 2 points are having at the same potential difference, right? And this is what I explained to you even mathematically, right? So this is important. Thank you very much. And inshallah, the capacitance, the topic, capacitance of a parallel plate capacitor, I will explain it to you in my next lecture. So see you there, inshallah, in the lecture number 10. Look, let me see here, stop.